Okay, so for week 6, we need to cover the reading behind the bending shear force and the bending moment analysis. What's interesting is that this kicks off with a very mathematical interpretation of the terms here. So here they're saying that the slope of the graph can be found in terms of the load intensity, and that the bending moment diagram in effect is, if we drop down to here, in effect is an integral of the shear force diagram. So these are the equations that kind of make a bit more sense to us. We've got the shear force, the Q value, is going to be all the weights that I can see. So I integrate from an initial position. That's what we're basically saying. So see how we would sort of doing that manually. We're kind of doing a manual integration. And some of you might have noticed that that your shear graph diagram then became something that looks very much like the integral of that diagram, and so that's what this introduction starts off with. And what's interesting is that some textbooks will actually try and solve these things using a very mathematical approach and using like all the integral symbols and all that sort of jazz, whereas this UE course tries to avoid using integration. So using this idea that we've got this line and we're looking left to us and we're adding up the values, and that we've got a pivot and we're calculating the sum of the moments. So this bit is interesting. Some of you that are more mathematically minded might want to investigate it more, but I wouldn't worry about it too much. Here we're talking more about the approach we're using at UE and the convention that has been used at UE. I don't find these diagrams particularly helpful. We just want to be aware that for our convention we are going to be using that if the force is going up, it's going to be a positive value on our shear force diagram, and if it's going down, it's going to be a negative. And we will be taking the fact that what is it that as if we imagine our pivot position, and if that's going to give me a be an anti-clockwise moment, that will be a positive a clockwise moment, that will be a positive value, while an anti-clockwise moment will give me a negative value. So using that convention, which is probably not so traditional, you see in the majority of textbooks actually kind of take it the other way around, but using that convention, that means that if we end up with a positive M value, we should be getting things that are sagging, and if we end up with negative value, then we should be getting things that are in fact hogging, so sort of like being bent upwards. So this explains how you want to apply your general rules for your drawing your diagrams. So that's all good stuff to read through. And this thing here, this point of contraflexure, so that quite often comes up in exam papers, and point of contraflexure is when the M equals 0. I think I don't think this is particularly useful, to be honest with you. I would kind of skip it myself. We've got the different types of loading and how we would expect they to have what kind of graph that they would then produce. What's confusing about this diagram is the fact that we've combined the M's and the P's. It would be nice to split them up, really. So if you ignore the M values, the bending effects, and just looked at the effect of putting a point load down, then we'd see that we would get a step change with a load and an integral, for example. Something I'm not really concentrating on is this turning moment effect. There's an Arnold screencast to watch there. I'm fairly sure it isn't going to be appearing in the exam paper or your Taoist testing and that sort of thing. So I think this is more of an exercise that you want to do for further reading. Sorry, I didn't realise we were sideways on, so we cut off the screen there. So that wasn't very good, was it? Anyway, getting back to portrait view. This point load example, so we've got an Arnold video on that one. He takes you through that example. And what's nice is that if you go to the book, is that you see the final plot of what this looks like. So you can see that we're getting an upward force there, so upward, then it drops 14, then it drops 28. So what you could do is notice what is the area of these values. So we've got 4 times 18. Oh no, sorry, there we go. Distance of 2 times 18. So 2 times 18 is 36. And then what's this area here? So you've got 3 times 4, so that's 12. 12 plus 36 gives me 48. And what's the area here? This time it's negative area, so it's going to drop. So we've got 5 to 7, so that gives me a distance of 2. 2 times minus 24 gives me minus 48, so 48, and I end up back there. So you can see how you can, for these simple cases, you can just look at the areas for your shear force and then just make them sum up the areas as you go along, and you'll get your bending moment diagram. Work solution. So I talk through the PowerPoint for this work solution, so that's on Blackboard for you to watch. Problem sheets, so we'll be doing that, doing these problem sheets 7 and 8. We'll tick them off so we can move on to a different topic for next week. This is the problem, this thing, something called a point moment, and if you want to, you could skip it. We might return on this topic towards the end, but there is a video there from Arnold who explains and takes you through it. And then I'm fairly sure there's a video here from Arnold for this one. If there isn't, then let me know. I will produce one for you. It's quite a complicated one. Work solution, made a video for this one, so I've take you through the PowerPoints there. It's a bit of a mammoth one, that is, over 30 minutes long, 90 slides to get through. And then again, a complex loading problem, and I'm not particularly interested in going into too much detail there, except maybe as a topic at the end if we have time. So that takes us then to the problem sheet. So the problem sheet 7, problem sheet 8 are the two that we ought to be getting done this week. Try and get them done during your tutorial if you can. So try and maybe tackle a couple problem sheet 7s, a couple from problem sheet 8 would be ideal. You notice that problem sheet 8 doesn't involve any point moment or what called complex loading problems, but it involves UDLs. So being able to do bending moments and shear force diagrams with UDLs and concentrated loads on is the thing that I really want to get ticked off.